Okay, so good evening. So we are here at the most important RL algorithm being used today, known as the policy gradient algorithms. Before we have discussed classification problems in the previous class, and we similarly will in the similar Mojo will be continuing with a few more classification questions, and I'll give you an idea of how models and neural networks can look like in general. It's a vast ocean in itself, but just knowing these will give you some foundation to start off with some project, as well as you can also go back and see the session 20 and 21 from JU 2024 Intro ML course. So there you will have a lot of perceptrons and detailed backpropagation algorithms and so on. Today also we'll be doing it in some detail, but what I'll do is I'll concentrate mainly on the a little more abstract view of it, and not go into nitty-gritties of every step of the update rules and so on, because our concentration is going to be on the policy gradient methods. So first of all, recall a classification model, say a K-way classification model. What do we need to do? Can you tell me? So it takes in an input. This is a feature vector. And this model, say it's the model is P theta. What does it output in a classification K-way classification model?
The class, predicted class. But
Is it or
no, it's the
correct?
probability distribution of the classes.
Very good. So we discussed this last time, that P1, P2 dot Pk, P theta of yi equal to K given xi is equal to Pk of the ith sample. This is what we discussed. This is the ith sample, kth class. And we classified maximum. So we said that y predicted is equal to argmax of pi. Okay, fine, great. So this were all fine with us. We did softmax using this was a softmax function that we use. But let us see, we discussed only linear algorithms. So we discussed that these data points were linearly separable. And today, where we'll be reaching to this is just to give you an outline. We will be trying to model the distribution like this, right? So this is also can be a classification problem, right? Given state, predict probability of actions. Same. Do you see they are the same problem? No problem, no
Yes, sir.
difference. Yes. So in RL, we do state, and this will be action. This will be class probabilities here. This is in RL. This is in normal ML algorithms. Fine. So what I'll try to do now is I'll try to show you that always linear models don't work. So we were saying all this while that our y was some function, say in binary classification problem, a sigmoid function of W transpose X. Yes or no? Do you agree? Fine.
Yes.
So W transpose X is a line. For example, if you have a 2D data, for example, if you say we have and data, that is, what does it mean? 0, 0, 0, 1, or sorry, 1, 0, 0, 1, and 1, 1. If we have this 4 data points, we'll say this is positive class, this is positive class, this is positive class, and this is a negative class. So we discussed last time that this sigmoid function, do you remember what this function was like? The sigmoid function was something like this, yes or no?
Yes, Dada. At 0, it would be half, and at minus
Correct.
infinity 0, infinity.
Good. So do you agree W transpose X is equal to 0 will be the decision boundary? So somewhere like this. This will be your W transpose X. See, when it is 0, it is on the line. You don't know. If it is on the line, you don't know which to predict. But if you are on either side, this side or this side, you know, right? This is the geometric view. Clear? So this is say greater than 0.5 and this is less than 0.5 or less than 0. For example, W transpose X is less than 0 and this is W transpose X is greater than 0, which means that Y is greater than 0.5 and Y is less than 0.5. Do you agree? Fine.
Yes.
For this problem, so what are the features? We have features are x1 and x2. Do you agree? So we want to predict, say y is equal to, this is equivalent to saying the sign of the function W transpose or W1 x1 plus W2 x2 plus b. Okay, if we have a function like this, we can predict. We'll see how. Say, for example, we want, what is the contingency table we want? Say x1, x2, 0, 0, 0, 1, 1, 0, 1, 1. You want the y to be 0, 1, 1, 1. Yes or no? Right? So let me choose and I'll show you a specific. There exists a W1. Say W1 is equal to 1. W2 is equal to 1. And B is equal to minus 0.5. So now you see y is equal to sine of x1 plus x2 minus 0.5. Does this classify the data? It classifies the data, right? So if you have 1 and 1, so let us try and write down required. So x1 plus x2 minus 0.5. This is minus 0.5. This is 0.5. This is 0.5. This is 1.5. Therefore, sine operation is minus 1, 1, 1, 1. That's all we wanted. So you can say minus 1 is class 0. No problem. Questions? Can I go ahead? Are the features and the predictions clear?
Yes.
Okay. So if that is clear, so let us try and understand this case. A case of an XOR problem, the very, very popular XOR problem, to show you that a single layer or a single, so this is, what does it look like? So this looks like in graphically, you have x1, w1, w2, x2, and you output y. This is called a perceptron because neurons in the brain often function like this. You have a lot of dendrites feeding into the axons, and then in these axons will decide whether to fire or not and transmit the decision to the next neuron and so on. So that's why it comes from this neuron. So the people named it perceptron late in the early 40s and 50s. So we'll see. Do you see here that a linear decision boundary like this will not work? Do you see in an XOR problem clearly from the geometry? Instead, we need something like this. Do you agree? To classify. So a single layer or a linear perceptron will create linear functions, as we saw, of the order W transpose X. So will not work. Clear? So what is the solution to this? The solution to this is defining two layers. So let us see what to do. So I'll just copy this diagram. Okay. Now let us look at this in a bit more systematic manner. So now if I can take two decision boundaries, so the idea is, this is the idea, two decision boundaries, a conjunction of two decision boundaries. Can you tell me now what to do, how to do that? What will be the two decision boundaries?
One would be the one we had considered earlier, and one would be one where the B would be uh, 0.5, I guess.
Correct.
Like just
That is
one
fine.
event.
One.
So
So I'm saying that the decision, let us geometrically first see, then we'll decide the functions. So if this is say for this line, we will say this side is positive. And for this line, we will say this side is positive. Fine. And I'll say wherever both are positive, wherever both are positive, I classify to be positive. Is this clear? This is what I have to do. Divide it into two tasks. Fine. So let us first decide one decision boundary first. So decision boundary number one, say this one. Say, I will say that this outputs something called as Z1, maybe. Let's see. So we'll input X1 and you will input X2 and say we will output Z1. Okay. So the inputs have the weight W. So I'll tell you slowly what these notations are, which will help you in perceptron as well. So the say is neuron 1 and this is neuron 2. We'll come to it later. So this is 1 1 and this is neuron 1 from 2 is 1. Okay. So my notation will be W I J for a layer n. So I is, tell me what is the output index, right? The first index, 1 over here, this is the neuron index, output index or the neuron ID. It is fine. What will be J? Input index. Okay. Fine. And L will be the layer number. So now please follow me, otherwise I'll not be able to understand. This is a bit of a calculation. So if you don't follow, it's going to be difficult. So say Z1. Z1 is again sine of W11 X1 W121 X2 plus B1 of layer 1. Is this fine? Similarly, Bi of L will have the same notations. I is this and L is this. Questions? I'm waiting. Is the linear combination clear of the features?
Yes.
Okay, so if I want for, this is my neuron 1, which will say positive for everything above it, right? Neuron 1, I want to say positive if either x1 or x2 is positive. So we already know the weights of this from and, oh, sorry, did I write and that? That one is and. Sorry, this is or. What did I write? You didn't tell me also. Okay. So both of them are positive from the or logic. So tell me, what will W11 be? 1, 1, minus 0.5? Yes or no? We can choose any minus, not a problem. It is fine. One of this is okay. Okay, if you have understood this.
This is the lower one.
Huh?
This is the lower one.
Correct, it's the lower one. Now Z2 will say positive if, see, that lower one is a bit critical. See, the lower one will say number 2 positive if at most 1 is positive. Correct? Do you agree? Yes or no? Fine. So we can do something like this. So let's say, look at this function. So again, Z2, tell me the weights that will be linking Z2. Tell me the weights. Can you tell me? Weight IDs, not the weight values, like just the IDs, like in form of notation.
Upper one will be W21
Yes.
because it goes to 2 from 1. And lower
Correct.
one will be W22.
And layer 1. Okay. Do you agree?
Yes.
Perfect. So what I understood is that for first we did the OR one for the case where the data was linearly separable. Now when the data is not linearly separable, we are doing first OR operation and here the two denotes an AND operation, and then we are gonna do an AND
Yes.
operation of the OR and the NAND.
Correct. That's the idea, but we are just geometric. That's a Boolean algebra way of looking at it. But we're going to show the geometry of it. That's right. Absolutely right. So now tell me, what would be the notation for this one? What would be the notation of W?
W11 of layer 2.
Very good. And this will be W12 of layer 2. Good. So now let's write down Z2. Z2 also is simple. So I will just write down the notation first. W21 layer 1 x1 plus W22 layer 1 x2 plus B2 of 1. Fine. So this is all right. Once we understand this, so I can do something like, look at this decision boundary that I have over here. It says that it is negative or 0 for both ones. Therefore, I can say that A dot B, as you were saying, NAND bar, right? Correct. So my idea for this line is trying to do is I can do something like say that I can do only and put a negative sign. Yes or no? This is equivalent to saying minus of the function for A dot B. Correct? If I am saying -1 as 0.
Yes.
Correct. So look at this. So now it is very simple. Once I do that, this is 1, this is 1, and this is, tell me a number.
-1.
Minus 1.5. Let us look at it and you will understand. See, again, x1, x2, x1 plus x2 minus 1.5, 0, 0, 0, 1. Or you can also put -1, not a problem. But it will not, sign will not come. We have put sign, no?
Got it.
1, 0, 1, 1. See, the first one will become minus 1.5, second one will be minus 0.5, third one will be minus 0.5, and the fourth one will be 0.5. This will give you 0 or -1, -1, -1, 1. Sign. So these are all zeros corresponding to zeros, but currently we don't even need this. We'll keep -1s. We'll take -1 happily, and positive if maximum one of the output is 1. So fine. So now I will just put a, what do I want? I want the opposite, right? I want this to be 1, 1, 1, 0 or -1. Yes or no? I want the opposite. So I will just put a negative sign. Sign of -f. Okay, so this is our function. Do you agree? Clear?
So like we can also think by the intercept, because we increase the intercept by 1. So it was
Correct.
0.5 earlier. Now
Yeah,
1.5.
any 1.1 and 1.2, anything would work. Intercept, we are moving it upward so that it does not cross these dots. Fine. So now I know Z1 and Z2. Your Y is sine of W 1, 1 of layer 2, Z1 plus W2 1, 2 of layer 2, Z2 plus B. So now I know, clearly see, which ones do I want? Both of them to be positive? Yes or no? Y is positive when both Z1
So
and
now I can do the AND ones.
correct. So here clearly I can do and. And is very simple. We have already done it. 1, 1 minus 1.5. Fine. So this is giving you an idea that when we increase input, especially non-linearities, do you see there's a non-linearity here? This is a non-linear function. Do you agree? Look at the sine function. The sine function looks like -1 and 1. And note, -1 is class 0. So some people may say that Dada, it's going to give me -1. I don't want 1. But that is a trivial rearrangement. 1 is class 1. So this is a sine function. Clearly a non-linear function. Do you see? Because there is a non-linear jump at 0. Similarly, there could be other non-linearities like the sigmoid function we have discussed. Sigmoid of x is equal to 1 by 1 plus e to the power minus x. There could be other non-linearities like the ReLU function. This is popularly used. This is max of 0 comma x, isn't it? So anywhere where there's not a linear function can be used. See, what will happen is these models will self-learn and set the weights, tweak the weights so that these decision boundaries are created according to the data. And we'll see how will they learn now. Okay, so let us see a general neural network, which is a multi-layered perceptron, for example. Any neural networks can be multiple types, but let us see a multi-layered perceptron.
But even though we introduce linearities, these are like for activation, right? That
These are activation, yes.
like we are just activating the function so that we can think of them as probabilities.
Correct,
But
but geometrically, what it does is it reshapes the decision boundaries, right? You can create any decision boundaries.
right, so even with logistic regression or like doing linear approximation, we can have around decision boundaries.
You cannot, because we clearly saw in logistic regression, it's a one layer perceptron. That's what I discussed here. No, so see, when W transpose X is greater than 0, it is at
Yeah.
class minus 1. W transpose X greater than 0, class 1. Isn't it? Not in logistic regression, decision boundary is straight. It's not going to be curved. Unless you increase one more layer into it, it will not create those non-linearities.
So, like, how does the this effect of activating it? Like here also we were doing sign, but then like it's kind of contradicting to me that like when we are using sign for the signal function for telling that it is in one class or the other, so there should be like, yeah, obviously it makes sense that it's not non-linear, but how does when two layers get stacked up then like non-linearity gets introduced? Like there also it is two layers only, like two linear layers which get added up, so it's now like a rectangular layer within which
It's not two linear layers. It's not two linear layers. No, after the first layer, we have a activation function. So the output of the first layer Z1 is W1 transpose X, isn't it? This is the non-linearity. Whatever function you choose. Now, what will happen is, if you learn W's accordingly, as we did learn just now, well, like we choose, for example, but in training, we'll learn the W's. These non-linearities will help you learn complex functions, as we saw. There's now multiple decision boundaries, curves, circles, and so on. See, this is not a linear. So had this been a linear, yeah.
When we for the first case for a single layer perceptron, even that we were using sign there, it was especially the output was linear. We were just so, but here we are performing the operation with the nonlinear outputs. So that's why the final output that we get has this nonlinear features of the because of this in between layer.
Correct. Because you have in between layer which changes a linear output to a non-linear output. That's why you have the problem.
Yeah,
you don't have.
If it was a single layer, even if we did any kind of activation function and return the output, it would still be a linear output.
The linear output depending on the function, it will be a linear output. Now, if you say that your function is outputted and then you make a circle with the output of the function, then you can definitely make a circle. But for a sigmoid function, it will not be, no. So for example, I'll give you an example. Say your neural network outputs are radius. Okay. And you say your prediction is the radius at radius r. Okay, one layer, just one neuron. Fine.
Yeah, okay.
And it outputs r, and you say your decision boundary will be x square plus y square equal to r square. You can always do that, isn't it? You just output.
Yeah, but again the function that we would be using for that would not involve like only seeing linear functions of x1, x2.
Correct. That is true because then you will have x square and things like that.
But here with like when we are having like only linear terms, even if we do a sine or a softmax or a ReLU or a sigmoid, then the output, even though like the outputs get shifted and become non-linear, but when we would just be then classifying, when we would just be classifying it, and so the effect won't be
Correct.
apparent. But when we would perform any kind of operation with those outputs, and then get predict the output for like here the XOR problem, then we can create more complicated decision boundaries. But otherwise, it would only be a line.
Correct. So see, the line is there. Line is only giving you a reference, and how far you are from the line will give you the probability. The decision boundary, the non-linearity in a logistic regression setting is just the conversion of the distance from the line. So W transpose X is basically distance from the line, yes or no? If you have W as unit vector.
Yes, it is the difference from.
Yes, so distance from the line is just change into probability. So it is far away from the line, then you will get higher probabilities of being in a class, right?
Yes, that's what we have been doing in the last class as well. We
Correct,
were
because that's the
doing
probabilistic view. But when you put the line as a decision boundary as a geometry, it's much simpler. So we have done the difficult thing, so a simpler thing becomes much easier. So when you have a line, if you have things far away from a line, we say that it is in a particular class, but I don't know the probability. When I don't know the probability, then this sigmoid function comes in to make it a probability. It's not essentially a non-linearity that is being leveraged in the network to make
Okay,
complex
I
decision
got.
boundary.
Yeah,
Yeah.
but when we stack up layer after layer after layers, we can create complex decision boundaries. Like even if we are using like in each step a logistic regression, then even then we could have an n polygon, and what if we
Correct.
keep increasing that n size, it could even be like almost like a
Correct.
circle.
That's the theorem that's called the universality theorem of MLPs or any neural network. That it is a universal function approximator. Any function can be approximated using a neural network. So the theorem we discussed, perceptron learning algorithm, by the convergence and so on last time. Universality of neural networks, they can approximate any function. So this has been proved for enough long neural networks, enough deep neural networks, and so on. So that's what you are saying. That is absolutely right. When you're saying that I'm going to curve the space, my decisions, my outputs at every step are becoming non-linear function of the previous state. The next step now gets the opportunity to curve the outputs like we did it here. So let us take an example of how we stack up multiple layers in a multi-layer perceptron. And what you said, I forgot to correct you. See, when you're putting sigmoid activation function in the intermediate layers, no, that's not actually a logistic regression. Okay, so that is just a activation function then. When only you are putting it at the last layer for making a prediction, that's the time it will be called a logistic operation. That's when you're using it for probabilities. In between, it's being used for introducing non-linearities.
Yeah, I just said that by logistic regression I meant the linear function like summation
No. You
wixi.
said no sigmoid. If I use sigmoid function for like the logistic sigmoid function in between,
I
that is
just
not.
was saying that even if we use summation wixi at each step,
Mhm.
even then we would be able to create and the complicated decision boundaries like polygons or anything. That's what I was saying
So you're
because they
saying
are.
only linear layers.
Yeah, I was saying that if we were that you said now that we are at every step we are doing this activation of W transpose X. So here
Yes,
W transpose X is a linear thing, but
correct,
and then the see activation is introducing the non-linearity, and then we are adding it again using
correct.
another W transpose Z, and then again an activation. So
Correct.
what I was just saying that even if even within this activation function, even if we are not doing any non-linear operations, even then we are able to create non-linear boundaries because the
No, you cannot.
activation.
Just try to multiply multiple matrices and see, you will get a linear function at the end of the day. See, y is equal to W transpose X. Fine. Y1. W2
Yeah,
say is without activation function. This is the linear algebra you need to know. Say W1 transpose X. And W2 is say W2 transpose X. Or here these are matrices, say WX and W2X. Fine. Or W2Y1, sorry. So now just put the value of Y1 over here, W2, W1X. This can be
that
written as an,
is okay.
it's a
Yeah,
linear
so
function.
so we are only doing the activation in the last step. So that's why only in the last step we are getting the non like probabilities. Like
Correct.
when at
I
every step
understand,
we are not.
but I understand, but you're saying you'll stack up, you have multiple layers. Let me draw it. X1, X2, dot, 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 say your D-dimensional features, XD. Layer L plus 1. Finally, to the output layer, Y. Okay, so you are saying all of these layers will have sigma as equal to the identity function. That's what you're saying?
Uh, no, man. Like I actually before that I actually thought that at every step we were using we were activating it, and that's how we were introducing non-linearities, and that's why I said what I said. Uh,
No,
so
you activated activations will only be used when you use activation functions, no nonlinear activation functions. Like
yeah.
we did, like we use sine over here. We use the sine and nonlinear function over here, no?
Yeah, and so like that's what I was saying that when we are using the sine functions, initially what we had as inputs became like
That
initially
is
we had.
fine.
Yeah.
That will be changed into nonlinear function. That will be changed into some inputs will be changed into some other inputs, which will be then fed to some other input. That is true.
Yes.
And at the end, you will be making predictions. But you also said that we without even using any activation function in between, like something like this, like first layer, second layer, and so
No,
on.
that's not what I was saying. I was assuming that at every step we were doing a linear sum and then doing a activation and then doing a linear sum of the activated linear
That's what we
sum.
do. That's what we do. We'll see that. We have not come to
Yeah,
it yet.
that's why I said that we could achieve every curve because we were.
Correct.
I didn't say that we were doing linear after linear after linear without activating at each step. I didn't mean that.
So it just came out like that. Like that's why I showed you this. No, that
No, it's obviously clear. If we like multiply matrix after matrix and don't activate it, then obviously it's going to be linear. And I
correct.
understand that.
Mhm.
Obviously, probably I said it wrongly, but obviously in my mind, I was just saying that at every step we were doing a linear sum and then doing an activation, and
Correct.
that's what I asked initially, right? And that because for a single layer we weren't using those activated functions, we were getting an output which was
Correct.
where those were not reflected, but here because we are operating on this
Now you're saying
activate.
correctly. Correct.
Yes.
Because you're
So
using this
that's
no.
why that's
Hmm.
why, because like at every stage we are activating it. So now with those, even what I actually meant was that even if within the activation function we weren't using any non-linear functions, because we were stacking up layers after layers and using activation functions within them, we were able to achieve non-linear
Correct.
boundaries.
Correct. Those, but
Yes.
That's just being abstraction of this, but each of the nodes will have two things. One will be a linear operation followed by an activation function. Right?
Yeah, got it. Like probably we just talked more than we should.
No, it's fine. It's always good to discuss. So let us see what it is going to be like. So W, say again, we'll be defining, say W. So first of all, X. Say X is an input in this space R D cross N, which means X is equal to X1, X2, all the way till Xn. So note that I am stacking the examples in column wise. Right? So each of xi is in some d-dimensional space. Fine. So this is the input. So next, so WL is we will define this as R NL plus 1 cross NL dimensional space. NL plus 1 is equal to number of nodes in layer L plus 1, and NL is number of nodes in L. Is it fine? So just concentrate on this block over here. So this will have NL plus 1 nodes, and this will have NL nodes. Fine. So let AL, now let us define, okay, let's define it. Let
Can you
A,
once repeat what is DN in?
which
DN
one?
in? Can you, can
D
you
is the
once repeat?
number of features. N is number of training examples. Okay. Clear?
Yes.
I'm stacking the training examples column wise. That's what I said. Okay. So now, so nodes in L plus 1, nodes in L. Next, what will I do? I will define ZL as, so let's define the base case first. Base case. Base case is easy. So tell me what would be W, first W. So say this is layer 0, layer 1. What would be the dimensionality for the first W?
N2 plus N1.
Correct. N2, or rather N1 cross N0. Layer 0, I said, no, first one. Which is N0 is d-dimensional, yes or no?
Yes, that should be D.
Correct. See, and now this is D cross N, so you get Z to be what? N1 cross N, right? So you have Z1, Z. So again, like it's becoming a bit of a problem. Let me put it on a superscript, Z1. And this is X is equal to Z0. Okay. And when I write subscript, it are training examples. Following the same notations. Okay, and then I define an activation as we discussed all this while. A1 as some function of non-linearity of Z1. So the recursive case will be, tell me what would be the recursive case? Z L plus 1 can be written as?
It can be written as W into
Yeah, tell me.
yeah, W into N2 here, N2 cross N1, or probably something more general.
NL
Yeah,
we have defined NL plus 1 cross NL.
Yeah, NL plus 1 cross NL into F of ZL.
Correct. That is AL, right?
Yeah, AL.
Plus, so plus there will be a bias term. That is, of course, we cannot just multiply W1 x1, W2 x2, dot, dot, dot. Why? What is the problem with this? Offsets from the origin will not be taken into account. Only lines from the origin will be modeled. So WL. B is the offset. Okay, so B is, what is the dimensionality of B? Can you tell me? This will be NL cross 1, NL plus 1. So again, if you're not following, I'll come back to this. And AL plus 1 will be F of, so this is say layer L at layer 1's activation function. You can use different activation function at different layers, no problem. So this is the end case, and say if you have L layers, finally what you're doing some classification or prediction, yes or no? Your AL has to be your predicted Y predicted, yes or no? This is AL, yes or no? Do you agree?
Yes,
You write a for loop, it's your Y predicted. So what you will do is your loss function L of theta is going to be AL, capital L, minus Y true whole square for all I. So let me write true I equal to 1 to n. So this is how you define a loss function or any loss function, A of AL, comma Y. It can be softmax, binary cross entropy, any loss. At the end of it, depending on the problem at hand, you can define the loss function. That is not the big point. The point is looking at this equation. See, the equation is something like this. So if you expand this equation, you will get ZL plus 1. Yeah, tell me.
Can you once explain the dimension of Z? Is how we are
Z,
getting that.
the AL's dimension is what? NL cross N? Yes or no? So this is NL plus 1 cross N. So this dimension number of training example just remains the same. So we are coming to that. Just look at this. I have L plus 1 equations. Do you agree? Because there are Z's dimension is L plus 1. NL plus 1 to be exact. Yes or no? See, W
Yes,
matrix.
NL plus 1.
If you see the matrix W, so this will be W11, W12, dot, 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 W1, NL. Yes or no? For the layer L.
Yes.
W21, W22, dot, 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 W2, NL. All the way to W, NL plus 1, 1, all the way to W, NL plus 1 WN or NL. Yes or no? Which is a NL plus 1, NL plus 1 cross NL dimensional matrix. NL plus 1 is a subscript. It can be 5, 6, 10, 12, 100, 2000, anything. Fine.
Yes.
So now it says that it has NL plus 1 equations and how many unknowns? Tell me.
And N, like
N
we have,
unknowns.
yeah, so NN plus 1 into N.
Not N. N is the number of examples which will be multiplied stack after stack. NL unknowns. So think of if N is equal to 1. Doesn't change anything, no? W A L. Training example 1. Training example 2. Dot 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 training example capital N. If I have, this is just linear combination of the columns of W, isn't it?
Yes.
So you independently take linear combination across all the columns. And you get n independent output. So it's like taking n. So if you have 100 samples training examples versus 10,000 training examples, equations remains the same, isn't it?
Yes.
So this is, for example, say look at this equation. So 1, 1. Say whichever example you're taking, for example, say 1, say some example J, W1, 1, AI, 8, 2J, and all the way till the end. W1 NL of A NLJ plus B L1. Did you understand where the B is coming from? And the NN plus 1 equation will have BL NL plus 1.
Got it.
And you will have all these equations stacked up in this matrix. And this is called broadcasting. See, this is an n cross 1 matrix, it's vector. So you cannot really add NL plus 1 cross n plus a vector, which is NL. So in Python and tools like that, when you have a cross 1, so it repeats this, it is repeated. So that you can compute the operations. Fine. Okay, so we understood what is the MLP. So, but now how do we learn? Do you see we have to learn all WLs and BLs? Yes or no? Which means that I have to do gradient descent on all of them. Yes or no? Correct?
Yeah, for L plus 1 into N plus 1 into Ln of those weights.
Correct. So for every T plus 1, sorry. And I'm writing wrong, sorry. For every layer, I have to do this gradient descent, and how do I do this is the question. For every layer, I have to do for all layers. You can do it using chain rule. if you start from the beginning and go to the end, but that is again an exponential complexity, very, very difficult. There is a dynamic programming approach of doing it called the backpropagation algorithm. That's what we'll be discussing now. Took Hinton, like Newton had done this like centuries ago, but until Hinton just gave this almost in the face algorithm, people did not find it. So let's try to do the backpropagation algorithm. And we'll take this example. So we have defined forward propagation. And we'll try to use this algorithm on this. I'll show you how it is done using DAGs, or directed acyclic graphs. Okay, so now this way dz dy you can do as homework. I will do dz dx. So now you see you want to find dz dx or dow z dow x. Have you done multivariable calculus 101? If there are two variables on which our variable depends, if you have to find the variable, how it varies over those variables, how do you do that? You take a chain rule across all those paths, isn't it? That is, you will take dz dv into dv dx plus dz dw into dw dx, isn't it? This is your 101 calculus.
Yes.
Yes, sir.
You will see all the paths, and here it is where this idea struck Hinton. Say, I have to see all the paths. Whenever I have paths, he thought about graphs, being a computer scientist. So let's see how did he do that. So let's first of all, if you are doing a neural network on this, you will start from x. Your x and y will be your inputs. Do you agree? This is what your inputs are. And in between the v and the w are the intermediate layers. Do you agree? So your x, first of all, gets converted to, say, a equal to v square. Then a equal to v square and y gets added into, sorry, x square, sorry, very, very sorry, to get v equal to a plus y, isn't it? This is fine.
Yes.
So this is equal to x square. This is equal to y. That's why I wrote down the first equation, v equal to x plus x square plus y. Similarly, the second equation I will write. I'll start from y. I will try to go to w. Tell me what will I do? So I can write this as y square plus 1 into x. First step, what will I do? B equal to, which only depends on y. Tell me.
Y square plus 1.
Correct. And then how will I get w?
X into W.
X into b.
Yes, sorry. X into, I was going to say B, but
Correct.
mistake.
Then last step, z is equal to 2v square plus w cube. Yes or no? No problem.
No problem.
Now you see what I can do. First of all, I will define dow z, dow v. What is the value of dow z, dow v? See, all of these terms I'm going to find out slowly, slowly. Dow z, dow v is 4v. Do you agree? Very simple from the So since it's back propagation, this is called back propagation. We will see how we are doing the back propagation. Instead of going straight, we'll come from the back this way. No puns intended. Dow Z, Dow V is, what is it? 4V. Do you agree?
Yes.
Great. So now also another variable I have. Do you agree? Dow Z, Dow W is equal to 3W square. Fine.
Yes.
Great. So now this 4V, I will try to propagate it backwards. See, so I need Dow V, Dow X. So Dow V, Dow X, how do I get? I have to really think about it. So let me think about it. Dow V, Dow A into Dow A, Dow X. Is it Dow V, Dow X? I'm trying to get this green thing. So first tell me then, what is Dow V, Dow A? Equal to 1. And what is Dow A, Dow X is equal to 2x. Do you agree?
Yes.
So see, what is happening is this 4V will get multiplied with 1 with 2x. And this entire path will give me Dow Z, Dow V into Dow V, Dow X. Do you agree?
Yes.
So just multiplying. So Dow Z, Dow V into Dow V, Dow X is just multiplying 4V into 1 into 2x. This is equal to 4 into V into or 8Vx is equal to 8x squared plus y into x. Okay. Similarly, I can go the other way as well. Dow W, Dow X is equal to B. Do you agree? Because I want X at the end of the day. See, now this can also go back through this route. So every route you went forward by, you have to propagate your gradients or your derivatives back through that route by multiplying them. So Dow Z, Dow W into Dow W, Dow X is equal to, what is it? 3W squared into B, which is 3
Y
into,
square plus 1.
yeah, y squared plus 1 squared into x squared into B is, what is B? I will get from the graph, y squared plus 1.
Square plus 1.
3y squared plus 1 cubed. So my Dow Z, Dow X. So this is exactly what backpropagation does. You can go from the last layer to the first layer by just doing these operations. And we'll take one concrete example just now, and I'll show you the derivatives in a matrix equation. Okay, done. So now let us try and find the gradient for an arbitrary layer in between. Okay, so this is layer L and this is L plus 1. Arbitrary layer in MLP. So once you understand this, this is backpropagation algorithm is very, very easy. All you need to do we are doing is calculating the gradients. So tell me the forward propagation equations here. ZL plus 1 is equal to WL AL plus BL. Do you agree? Right?
Yes.
And AL plus 1 is FL plus 1 of ZL plus 1. Agree with this also? So now if I remember what is our goal, what do we want? We want dow L, dow WL, comma, dow loss function, dow BL, correct? These are the two things we want for all layers. Right? So let's do it. First of all, tell me dow Z. So firstly, I can do dow L, dow WL. Say I am being given something from the next layer. What was I being given? I was being given gradients of the next layer, right? Say I'm being given L plus 1. Right? So this is being given to me. Now DL, DW I want to find. How do I find? So first, can I write this as DL plus 1 into dow ZL plus 1 into, these are all Jacobian matrices. We did it in detail last time, but I'll just show you what I'm doing just in terms of derivatives. Is this correct? Is this okay? If I know DA plus 1, and I know I am being given it back from the next stage, can the W be computed, the gradient be computed this way? This is from next layer. So this is fine. See, L, A, Z, sorry, Z, W. You're not following. That's why you didn't correct me. This is fine. Questions? What happened? Not clear?
Just could you just like after the let's consider the last layer. So we would be
Last layer
doing
we will see. Let us see the first. Let us see a middle layer. Last layer is very easy. First, tell me a middle layer. I
so
am
from the like L plus 1th layer, we are getting the DA plus 1. The
correct.
chain rule is okay. The chain rule we are the DAL plus 1, DZL plus 1, and the DZL plus 1 and the DWL are we calculating like at the middle stage, like here?
Correct.
In
This is being calculated at stage N. That's what we did here. No, clearly, if you clearly follow these algorithms, I did an analogous thing. I calculated
yes.
at every step. This is being at stage L. This is from next stage. This is the beauty in L steps. You can literally go back the entire neural network and finish it off instead of doing for every layer going forward like quadratic exponential number of times of the order of the functions.
Yeah,
Similarly,
instead of doing like doing gradient descent from every NL plus 1 into NL weights, we would just go back and
correct.
calculate it.
Correct. We can see for the first time if you have F, G, H, and so on, you can always take derivatives in the forward pass like F dash, G dash, so on, all the way to the end. Also, you can do is take the innermost derivative first and then go all the way backwards. That is faster, much faster, as you can clearly see.
Yes.
AL plus 1 into DAL plus 1. Where is it? Tau ZL plus 1, tau ZL plus 1. Your homework is to find out these values, find out the exact values. You can look at last time's videos also and try to find out these exact values, because there's the matrix calculations involved over here. So therefore it will take one full next 50 minutes to do that. So it's not good waste use of time since you have already understood what is going on. Similarly, now what is the responsibility of this current layer? Can you tell me? Current layer, what's the responsibility of it? I have used something from the future layers, and I have some responsibility to my predecessors as well.
Pass on that value only with layer L.
Correct. Very good. I need to pass on. This is how recursion works. I have to do this. No, I have some responsibility. I just can't say that I have used your value. I cannot. This is why I didn't go start from the last layer. So now tell me what will be dow z dow L? Same thing, nothing different. Clear? And this is to previous layer. In the last layer, again, base case, the loss is a function of AL and Y. This is your J theta, say the loss for the parameters. So dj or dl, dA capital L passed to layer L. Clear to everyone? Fine. For example, AL minus Y whole square. You'll just do 2 into AL minus Y, isn't it? Clear? No problem. Questions? Okay. This is what is the backpropagation algorithm. Please go back and try to know if you're interested, know and learn. And last time we have also implemented this in class after discussing, isn't it? Uthrij.
Yes.
Okay, so now all these things are done. So today in the next few minutes, I will be discussing how to learn we will be proving the policy gradient theorem and try to discuss one algorithm called the reinforce. Once we have done this, this is like a few minutes based on RL and ML knowledge. This is like a very, very easy thing to do. So again, recall, what do I want? I want my states to be given to my neural network. So now it can be a multiple layer neural network with a k-way classification. Do you see everything falling together? Which will give me a probability over actions. Yes or no? This is what I want. Say an MLP. Questions? Linear layer will also work. So last layer could be a softmax layer. So which says that pi theta of S given A. So we are trying to learn pi theta, which maps from states to a probability distribution over actions. Theta is the model parameter. So we have abstracted out the entire, see, now there are two things. We know how the neural network optimization works. We know how the probability of a classification problem works. We now say that we forget about neural networks. Neural networks optimization is a black box tool, which we have already learned. We are now just going to think that this is the function that gives me probabilities. Is the abstraction clear? And once the neural network comes, I will give it to that black box. The black box will do the optimization for me, as I discussed previously. This is how you must think. In one of our classes in UG, a professor of us, I think Professor Shomiron, I don't know if you have taken his class, he was telling when first compilers were made, what do you do first? This is a good story to keep in mind. You first write the machine level language, whatever binary language. Then you write on the top of it assembly level language. The assembly level language, once you've written, you write further bigger languages. So you think that these are already known. So you use a larger abstraction. So finally, you use object-oriented algorithms, which in turn use very low level, in turn use much already defined predetermined algorithms, which are already written in the classes. So you can keep building on stuff which are already there and not every time think of the components which are large in itself and are self-contained. So here the neural network itself is self-contained, and we will think about it only when we are going to write down the final objective or when you're implementing the final objective. Is that clear? The philosophy clear?
Yes.
Okay. So now recall, say R of theta be the objective. What is our objective in RL? Say T is the steady stochastic shortest path problem, which is a T state. So anything between 0 and 1 will work. Si, AI, Si plus 1. What is the objective? Can you tell me? The objective of RL is, again, to maximize long-term reward, yes or no? So your value function could be, or your loss function L theta could be the expected value of R0 or R theta. Do you agree? No problem. This is what I want. I want to maximize this. So the objective is theta star is argmax over theta of R theta. Yes or no?
Yes.
Questions? Okay, very good. So if you have understood this, tell me what next should I do? See, now your RL knowledge you have to use. Tell me what should I do next? I do not know the value function directly. What do I have to do first?
I need to do estimation using like
No. I will want to do something like conditioning and then take an expectation, say over a state selection policy S. So this is an iterative expectation. Do you agree? So say mu is a distribution to choose states. Fine, clear? Independent of theta. Clear? So now, since you're all experts in RL now, tell me what is this? This is mu of S over all S. And what is this? R theta given S. Do you know this function? You already? R theta given S is equal to S. You already know this. See? Summation of I equal to 0 to T gamma to the power I. R of Si, AI, Si plus 1. The expectation over. Do you know this function? What is it called?
the value function.
Very good, the value function. So this is basically your objective function is nothing but this, the expected value of your value function. Clear to everybody? Remember your policy is decided by neural network. Okay. So now what is the value function related to the Q value function? Do you remember? Do you remember how we have to bring in the policy itself, right? It does not depend on the policy. You have to bring the policy somehow. Again, the expected value of R theta given S0 is equal to S, A0 is equal to A. I can do this.
Yes.
And take an action probability distribution over these over the actions. So we recall this is equal to pi theta of S comma A. This is the first class of our classes. Sorry, I wrote the opposite. A given S, A belongs to A, S belongs to S. Correct? Agreed?
Yes.
Very good. So now I know my objective in terms of theta. Very good. I know my objective. Yes, I'm done. Halfway done. What do I need to do to find out the best parameters theta? The objective is to maximize this loss function. Yes or no? So I have to do gradient ascent. Theta t plus 1 is equal to theta t plus alpha t dl d theta. Do you agree?
Yes,
That's all
Dada.
yes. So all I have to do is again take gradients. That's it. Take the gradient. See the first function. This is independent of theta. So I get summation of mu s gradient of summation of A belongs to AS pi theta of A given S q pi theta. For the time being, I'm not going to write theta for ease, but I'll let me write it. Okay, so fine. So let us try to see the derivative of this inner function. Are you okay? Are you okay with me? So the inner function is v pi theta of S. Do you agree? Time and again we have proved that. So let us take the derivative of. So this is done. MDP is done. Now let us try to take the derivative of the inner function. Let us try. In case you're not following, please stop me immediately. Agreed? Now I want to form a recursion again. In RL, what I was doing, whole of RL, I have been forming recursions. Yes or no? Let us try to form a recursion. How do I form a recursion? Bring in states, value function again from Q value function. Do you remember? Please, this you should tell me now. After 20 times at least I have derived. What should I
Yes.
do? Tell me.
So I can write a like you want the next value function, right?
Yes.
So expected value of reward plus
Tell me, what can I do?
yeah, expected value of reward of a dash plus
Okay.
the value
This
plus
I
the
all. This is the Q value function. This is fine. The first step. Wait, I'm writing the. It's not yet coming to the screen. The screen struck, no, at expectation. Now it is here.
now it came. Yes,
Yeah.
so again here it would be r plus gamma into v pi of s dash.
Correct. So this plus gamma times V pi of S dash, given S and A, the expected value. We have derived this again and again. So this is basically writing out the first reward, reward 1, and then the summation of I equal to 1 to t, taking gamma out, S t a t or t plus 1, and using homogeneity, right? Homogeneity of Markov chain. Right. So I will write this as, again, the full expanded equation will become pi theta of A given S, summation of your control Markov chain, S dash in S, reward of SA S dash, plus gamma times V pi of S dash. Do you agree?
Yes.
This very nice. So now since we have agreed to this, all of us, let us now use chain UV rule to differentiate it properly. So if I differentiate it with respect to first with respect to pi of theta, what do I get? Okay, I get the derivative of pi theta of A given S, q pi of SA. Do you agree? This whole thing is q pi of SA. Yes or no?
Yes.
And the
Yes. So
second one,
we just
yeah,
have
tell me.
yeah, second one we are gonna differentiate the when in effect we would be only differentiating the V pi
Correct.
theta
Very
S
good.
dash.
You have understood. That's clear. So if you differentiate, if I differentiate with, I'll keep this fixed UV rule. D of UV, U dV plus V du is what I'm doing. Pi of S dash is a derivative of, I have a gamma as well, V pi theta S dash. We got the recursion, yes or no? Fine.
Yes.
Tell me, what is this a function of first? Just, do you agree this is a function of S dash? Or sorry, S? We are summing out all the S dashes and all the A's.
Yes. It's obviously a function of x.
I just keep for the simplicity of equation, I will write this as f of S. Can you now help me write down, expand this S dash? So let me write down one step first and then you help me.
Like it would become policy of A given S dash into Q of S Q of S dash A sum over we would be summing over obviously all the actions again if we write in terms of
See, this
Q.
is it is V delta V theta of S is this equation. Do you agree? The gradient
Yes.
of, so your V dash would also be the same equation by recursion.
Yeah, we by recursion the same equation again and again. Like
Correct. So let us write one more time. S dash. So this, I will just replace the order of summation for our, in a minute you'll understand. Pi theta of A given S, E of S dash given S A. Then I'll get, in the internal, I'll get F S dash plus the summation over all actions. So I'm writing down this same thing here again here. Please follow the algebra. Both these things, I'm just putting these equal to values. gamma I theta. Let's write this as double dash A dash given S double dash P of S double dash given S dash A dash gradient of V pi of. Clear? This is correct?
Yes.
Everything okay. So now if
So
this is
like
correct,
pi theta of A dash given S dash equal.
S dash ठीक बोले थे perfect, correct. So you are all following, very good. Pi theta of A dash given S dash. Next state, correct, very nice. Just writing error. So this one, the first equation becomes Fs plus. Now tell me over actions, what is this called? We have discussed this again and again. This is yes or no? We are summing over all the actions by Bayes rule, law of relative probability. So this is like S dash pi theta. I will write 1 on the numerator for one reason. I'll show you next. If S dash, okay, plus summation of S dash. Again, this internal equation also will be the same. Gamma square. Or let me write gamma square outside. S dash S double dash P pi theta of S dash give from S pi theta of S double dash from S dash. Is this correct?
Yes, Dada.
This entire thing, this thing I summed up to be P S double dash given S dash.
Got it.
So yeah, if you have got it, now you have to tell me what does this actually mean? Or do you see that this is Fs plus gamma times P pi of. We have discussed this in Markov chain. S dash plus gamma square S double dash P of S double dash from S in 2 steps pi theta of gradient of V pi of S double dash. Do you see that? If I reorder the summations, previous summation, I write this as S double dash and this as dash. So basically what you're doing, you're taking 2 steps.
Yes,
See the
two-step reward, make not two-step reward, but yeah, 2 steps.
2-step probability. Moving to S double dash from state S in 2 steps. S to S double dash. This is through all the states, possible states, isn't it?
You just wrote the Bellman 2 times.
Yes. We have written the matrix of Markov chain 2 times. Very good. So now this, if I go on unrolling till infinity, what can I write? I can write this as summation of S dash belongs to S, k equal to 0 to infinity, P pi theta k in k steps, S dash given S, gamma to the power k, f of S dash, isn't it? See here, you did not have anything. You had 1 with it. Here you had this function, which is just 1 step. Then we had 2 steps, 3 steps, and so on. All the k steps. Just reordering the summations. Is this clear?
Yes.
I'm waiting a moment. If you have a question, please ask.
And
See,
no,
k
the P5 of that above K resolves the issue, everything.
yes. So this k is in k steps. So now let us look at one thing. So this is our gradient of
What
V pi
what
of
happened to the remaining term?
remaining term.
That V pi of S dash.
This one,
The one where, yes.
double dash, you mean? This will again be
Yes.
expanded. No, this will again be expanded to get 3 steps. This can again be expanded
Means
using
in
the
the
same
last,
equation. In the last, you will not have it because you're putting it to infinity. No, in infinity, that goes to end of the, that is 0. End of trajectory. V pi of S is 0, isn't it? That's how we are getting rid of
yes,
gradient of V pi, which is a very, very critical thing in the policy gradient algorithm. Many books will not tell you this. They will just say that it's not a function and so on. So now, again, our L theta is what we defined, I think, is it? Yes, L theta is what? Summation of S dash in S, k equal to 0 to infinity. Let's say gamma equal to 1 for stochastic shortest path problems. So that is episodic task. We know that the episode will end. So p pi theta to in k steps, S dash, f of S dash. Okay. And what do I have? I have mu of S. Yes or no? Remember, we were seeing only the internal function. Yes or no? Wait, it's not coming yet. We only saw this internal function that I have boxed. Correct? We found only the gradient. Therefore, gradient of L theta will be the entire thing. Yes or no? Questions? Clear? I just put the value of V pi here.
yes.
So now if I put all the equations together, S dash in S, k equal to 0 to infinity. So it's from S to S dash, sorry. P pi theta of k, S dash to S, mu S, summation of mu S is, I am reordering the summations, and f of S dash. This, do you agree, is just P of S dash in k steps? I am summing over the initial distribution. Yes or no?
Yes.
Initial distribution, and this is to go to S dash from S in k steps. So this is saying that in k step, what is the probability you will be in S dash, right?
Yeah.
So I will write this equation again as S dash in S, summation of k equal to 0 to infinity. Again, this term again we have discussed in class. What is this term? Do you remember? If I divide this term by k equal to 0 to infinity and over all S dash in S, can you tell me what will this term become? So the numerator is, do you agree? Average time spent in is proportional to the average time spent in state S dash, because it's the sum of probabilities of S dash. Right?
You're right.
And if I divide by the total thing, then it is what distribution? This is the definition of the stationary distribution.
Yeah,
D,
nice.
the stationary distribution of the Markov chain. That is fraction percentage of time spent in state S dash. So I'll just denominator, I will maybe write double dash for you to understand. S dash in S, f of S dash. Oof, so nice equation came. See, the gradient of L theta. Do you remember what this Fs was? Do you remember? This was the gradient of pi theta of A given S, q pi of SA. Yes or no?
Yes.
See, the origin entire V term just vanishes. So many of the people who, when they tease this, they tell that this does not depend on theta and so on. And so you can do whatever you want. You can just take the gradient of the first term. D pi of S dash. Rather, let me write S. Fine. So this becomes the expected value of S being sampled from D pi, the gradient of, but still I am not totally happy with this. I have not got an expectation inside. I cannot use my popular SGD algorithm. Can you tell me how do I bring expectation inside?
Yes, like essentially I am taking an expectation of over the actions, aren't I? Of
But
QS.
you have a gradient. That's the catch.
That's
You have
right,
a
sure.
derivative. You have a
So
derivative. Yeah.
like can't we use like a lotus like or no
Divide
we
and
can't.
multiply. I have taught you already, no? Whenever there is a problem like this, divide and multiply. Okay.
Yeah, got it.
Now, if I divide and multiply, things become very easy. See why? So now I get an expectation over actions chosen from pi theta, the theta distribution itself, which you are learning. Similar algorithms are in AI, ML also, in generative modeling. It's called energy-based models. You get similar, very similar algorithms. When you will learn those, you will see that you will remember that I taught you this. See, I got this. Now do you know
Yeah,
this?
now I can do STD.
You can do SDD, but I can also do a bit more simplification here. What simplification can I do? Arey Baba, gradient of x or dx. How do I write it? F dash x by fx. How can this be written as? Log fx derivative, no?
Yeah, we can write it as like the D ln F.
Yes. So you in the softmax layer, you will have a log. That will even help you if you take a log because it has exponents. So that is even better.
Yeah, that's nice because we won't get exploding exponentials.
Correct. And you can directly take with respect to the log function itself. Pi theta of A given S. So therefore your algorithm is theta t plus 1 is equal to theta t, wherein is GD plus alpha t q pi theta of S comma A gradient of log of pi theta of A given S. So now people will ask, but how do I estimate q theta of this? I will estimate is one of the problems. So we have defined the policy gradient theorem. we will next class will be the last class where we'll be discussing actor critic method, but will be one method. Today we'll be doing what is called the reinforce algorithm. So the reinforce is a DP based dynamic programming based algorithm. Let us do it. Reinforce, generate a trajectory by sampling AI based on state I. So you get a status trajectory A0, A0, reward of S0, A0, S1, S1, A1, and so on. Yes or no? Correct? So from this, I can have an estimate of GT for given every state and action. Yes or no? This just be the sum of the rewards. Such that SI or S1 is equal to S and A1 is equal to A. Correct? I can get this value from the trajectory itself. You can do dynamic programming, get it backwards as well. And then I can just do theta t plus 1 is equal to theta t plus alpha t. GT, you can also put a gamma. If you want to learn and gradient of log of pi theta of A given S. If I put gamma in here, then I don't even need to put the gamma. Clear? Questions? I'm waiting. So this is called the reinforce algorithm. Iterate until convergence. So next day, what we will see a joint optimization of TD0 algorithm and the reinforce algorithm, the policy gradient algorithm. And then we'll probably do some planning, and that will end all the RL that I know, everything probably, which is required to do begin on any of your research or any course that you want to take. Questions?
So like when we were estimating say the GT using Monte Carlo in a like earlier lecture of say model free based
Same
TD.
thing you will do here, same
Yeah.
thing.
So we are for every step we are generating a trajectory, and for we are just adding all those GTs, right?
Correct.
And estimating those GTs.
GT equal to reward. So if you want to know GT minus
So
1 is equal to
that's how
GT.
I am finding the Q line,
Same,
right?
same.
Yeah, you did this in lecture 12.
Correct. So if this is now trivial for you. I didn't even write it very rigorously. That's why, because we know that we have a end state ST. I will just go backwards. ST minus 1. And I know I have taken an 18. No? This is how I'll go back and I'll keep updating thetas. Fine. Clear?
Yes.
Okay. So that ends policy gradient basic algorithm, and we'll do actor critic. We'll see a very interesting way. So do you see now that we did a similar algorithm in bandits, but now we have the algorithm in terms of states as well. So that completes a very nice circle. So nice. We'll see you for the last class on Monday. And then the rest of it will be, if we required, we'll go through the assignments. I'll share the solutions of the assignments, and that would be the course. We'll see. After that, you can get your certificates and so on. So, okay. So If you have no other questions, I'll stop for today and we'll see you on Monday. Okay. Stop recording.